This is our demonstration on DistilGuard, a large language model-based reasoning for assessing model poisoning attacks on federated learning systems. We'll start with an introduction to the challenge we aim to address. Federated learning enables training without sharing raw data, but it is vulnerable to poisoning attacks that degrade model accuracy or inject bias. Existing defenses depends on fixed rules, simple assumptions, or computationally expensive techniques. Our approach reframes detection as a natural language problem for LLMs. This is our proposed architecture for DistilGuard. DistilGuard is designed to identify and eliminate malicious clients in FL systems, which are vulnerable to poisoning attacks that can degrade model performance. Unlike traditional defenses that rely on fixed statistical thresholds, DistilGuard uses DistilBird, the LLM that allows to capture complex patterns in client behavior that conventional methods often miss. As you can see in the diagram, on the left side, we have the configuration panel where we can select the attack types, datasets, and attack settings. In the middle, we see a typical federated learning setup. The clients send their model updates to the server. Here is also where our defense system comes in. We extract statistical features from these updates, convert them into natural language, and then use our fine-tuned LLM to classify the clients as malicious or benign. On the right side, any malicious clients that are detected are eliminated from the aggregation process, ensuring that only benign updates contribute to the global model. Now, in terms of our simulation setup, we built our attack simulator on the Flower Federated Learning Framework. We conducted experiments on datasets including minis, fashion minutes, and 5G NIDD. During training, we extracted distributional and similarity matrices from client updates, converted them into natural language format, and then fed them into fine-tuned LLM classification. As the next step, we fine-tuned a DistilBird model for detecting malicious client behavior. Before training, we performed pre-processing steps such as dropping irrelevant columns and normalizing features with the min-max scaler. For training, we used Hugging Face Trainer API with DistilBird configured for sequence classification. To make the fine-tuning efficient, we adapted parameter-efficient fine-tuning through low-rank adaptation. This allows to update only a small subset of model parameters, significantly reducing memory and computational costs while still maintaining strong performance. The fine-tuned model is then integrated into our malicious client detector. The pipeline begins with feature extraction, where statistical and similarity features are collected from client updates. These features undergo the same pre-processing steps as training data, including min-max calling. Next, we encode the client behavior by tokenizing the feature descriptions and then feed them into DistilBird, which classifies each client as benign or malicious. Clients identified as malicious are flagged and excluded from aggregation in subsequent training rounds. Finally, verification matrices are used to ensure the detection system remains accurate and reliable over time. At the core of our project is a configurable simulator that lets us control federated learning training. We can select the dataset, number of clients, training rounds, and batch size. More importantly, we can enable or disable different attacks, choose the attack type, such as model poisoning or label flipping, and adjust parameters like which layers are affected, attack probability, and noise patterns. The simulator supports DistilGuard defense. We can activate the malicious client detector and then analyze the updates, flags malicious activity, and removes compromised clients from the application. Throughout the process, the detailed logs are recorded, and after training, plots are generated showing model accuracy and loss with and without attacks or defenses. Now let's move on to the results with our experiments with DistilGuard. Here, we first look at the system without defense. You can see the accuracy plot. Initially, the accuracy spikes in early rounds, but then it drops sharply and becomes unstable. This behavior is caused by the presence of poisons in the training process. Next, let's look at the same setup, but with DistilGuard defense enabled. As shown in the accuracy plot, the model training stabilizes, accuracy improves steadily and avoids the sharp drop you saw earlier. In summary, these plots clearly illustrate effectiveness of DistilGuard. Without defense, the model becomes unstable, but with defense, the training remains stable, and accuracy improves. So that's it about our research work, and thank you so much.